Okay, then I'm welcoming Christian William from UC Riverside, and he will be speaking to us on logic in 2D, metalogic in 3D, and the language of category theory. Thank you. Go ahead, Christian.
Thank you. Thank you for being here, and thank you to the organizers for the opportunity to speak for a third time. Basically, 2 years ago, I came and gave a talk and said, I have this big dream for a unifying visual language for category theory, but I don't know how it'll work yet. And then a lot happened over those 2 years, and I figured it out. So now I'm excited to present my thesis, which is logic in 2D, metalogic in 3D. So the thesis can be found at this link here, and it will be on the archive soon. Category theory is known as the language of mathematics, and recently applied category theory is developing it as a language for all kinds of science. But what is category theory? Why is it so effective in unifying all kinds of math and science? I propose that category theory is simply the language of thinking, because every kind of thinking is some kind of connection and transformation, and category theory is simply the general language of connection and transformation. So specifically, the language of categories is systematized in a two-dimensional structure called a bifibrant double category, also known as a proarrow equipment. And this structure can be seen as a logic, as in a system of thoughts of a world. And my thesis defines the three-dimensional language of all bifibrant double categories, and this can be seen as metalogic, or a language of thinking about thinking. So the fundamental notions of category theory are systematized in the language of this structure that is currently known as a fibrant double category, proarrow equipment, or also a framed bicategory. And we can understand this structure as a logic. So it consists of a category of objects and vertical or tight morphisms, which can be understood as a world of types and processes. And depending on pairs in that category, is a category of horizontal or loose morphisms and squares. And these can be understood as thoughts of the world, or a category of relations and inferences. So notice that I'm not talking about ordinary double categories. This adjective bifibrant refers to the notion of representation. So the bifibrance of a double category is the action of processes or vertical morphisms on relations or horizontal morphisms, pushing forward or pulling backwards in time. So for example, a function induces a graph or a cograph relation. A functor induces a dual pair of profunctors, and we use these all the time. And what I want to emphasize is this property-like structure is essential both for the expressiveness of a logic and the coherence and expressiveness of metalogic. So in a logic, in a language of categories, the notion of a representable profunctor is essential to define the notions of limit and colimit, as well as the Oneida embedding and other fundamental ideas of category theory. But also, for the three-dimensional meta-language of all of these structures, this bifibrance is essential to the coherence of that structure. Ordinary double categories do not form a triple category. They do not have well-behaved notions of, they do not have a well-behaved notion of profunctor, because composition by an arbitrary span of categories does not preserve colimits. So there is not a well-defined monad construction. But when you have this bifibrance, the span of categories of relations over pairs of types is, it's a fibration, which in particular is exponentiable. So composition by these spans preserves colimits, and you have a well-defined three-dimensional monad construction. So the main idea of my thesis is that these bifibrant double categories form a coherent three-dimensional structure, which essentially can be understood as a bifibrant triple category without interchange. And there's an important reason that there is not interchange. So my thesis introduces three-dimensional string diagrams, which is the only way I was able to wrap my head around this structure. And the idea is that if in 2 dimensions this is an inference, the idea is that this is a meta inference, which can be read, the third visual dimension is inner to outer. And you can read this as a square in one double category is flowing outward to become a square in another double category. So this is a picture of a general cube in this three-dimensional category. Each of these colors is an entire logic, an entire bifibrant double category. The downward pointers are vertical profunctors. The horizontal strings are horizontal profunctors. And the transversal direction coming out towards you is double functors and double transformations. So the thesis introduces this three-dimensional language, which I believe can help everyone to work on this very large and powerful level. But also, I propose that string diagrams and syntax combine into one language. Normally, we think about string diagrams as like an alternative representation of category theory, but actually because they are dual to each other, they fit together perfectly in one language, which I'm calling color syntax. And the idea is that a string diagram represents a general concept, and then substituting syntax in the string diagram determines a specific instance of the concept. So in particular, a string represents a span of categories, and then substituting a pair of objects, literally writing a pair of objects in the colors of the categories, determines a fiber of that span of categories. So this allows you to zoom in and out from a whole logic to the category of relations between a specific pair of types. And this equivalence between these perspectives, between the total structure and the fiberwise structure, is the basic principle of dependent category theory. And it's kind of remarkable that this principle seems to be immanent in the very idea of combining string diagrams and syntax. So this is the visual language that my thesis is using. So now, how do we actually, how does this three-dimensional construction work? So the key to the construction is an analogy between logics and categories. So a category is a matrix of HOMs with composition and identity. And in the same way, a logic is a matrix category with composition and identity, meaning for each pair of types, there's a category of relations between them. This phrase matrix category is short for two-sided bifibration, having to do with these actions of the base category on the total category. And then a bifibrant double category can be defined as a pseudomonad in this, this world of matrix categories. So that is what I will define today. But one last quick point, because there might not be much time at the end. The language that you get is very powerful because matrix categories are exponentiable. Not only is the construction coherent or well-defined, but also the language that you get is higher order. The co-descent calculus is the higher dimensional version of the co-end calculus. And the idea is that these matrix categories are higher dimensional versions of profunctors. So their composition is like a co-end, but instead of co-equalizing for associativity, you are adjoining an associator isomorphism, and this defines something called a co-descent object. And dually, for transformations between matrix categories, these are formed by a descent object. And these are dual in the same way that coends and ends are dual. So here, for example, is the derivation of the formula for a right extension in matrix categories. So this is an extremely powerful language in which you can systematically derive double-weighted colimits and much more. So here is the outline. Today, because time is limited, we developed the underlying structure of a logic, and then at the very end, the three-dimensional structure is essentially the monad completion of this structure. We basically just reap the rewards at the end. So the most basic underlying data of a logic is a span of categories, a category of relations and inferences depending on pairs of types and processes. And we review the equivalence between these spans and matrices, also known as displayed categories, while introducing the three-dimensional visual language. Then this span needs to be equipped with pushing and pulling actions by the morphisms of the base categories. So to do this, we need to determine how a category forms a logic or a bifibrant double category. And it turns out that it turns out that you need to define the coproduct of the arrow double category with its opposite. You need to form this union so that arrows point both directions so that you have both companions and conjoints. And we call this structure the weave double category. And then a matrix category or two-sided bifibration is a bimodule of these weave double categories. So this is what we'll review, and then at the end we can say, well, a logic is essentially a pseudomonad in these matrix categories. So, all right. So like I was just saying, the basic data of a logic is a category of relations and inferences over pairs of types and processes. So the first basic structure we need is spans of categories. So it's been known for a few decades now that inverse image along a functor defines a displayed category, which is a normal lax functor from a category to the double category of categories. And the idea is that for each, for this span here, being a functor into a product, for each pair of objects, there's a category of objects lying over it in R. And for each pair of morphisms, there's a profunctor from one fiber category to another. And in this way of drawing it here, it's already suggestive that the objects of a span category are representing the relations or horizontal morphisms of a double category. And the morphisms are representing squares or inferences of a double category. So the structure on this data of composition and identity is where we begin to enter the third dimension of this visual language. So composition of a span category can be drawn as follows on the left, and you read this from inner to outer. And it says, given a composable pair in R, represented as this composable pair of beads here, their composite is this outer bead, and it lies over the composite of the pair of morphisms in the base category. So you read it from inner to outer here. And this defines, when we're breaking up composition of R fiber-wise, this defines a matrix of transformations. So this is the lax part of this map from A times B to cat. And similarly, given an object over a pair A and B, its identity lies over the identities of A and B. So this defines a normal lax functor. Now, similarly, we want to define relations between dependent categories. So, in fact, we can follow this exact same idea of inverse image for spans of profunctors. And as far as I know, this hadn't been done, and it's a bit surprising because it does work in the exact same way. The idea is for each pair of heteromorphisms in the base profunctors, there is a profunctor from one fiber category to another. Other than that, it works exactly the same way. And what this defines is a matrix of profunctors from the matrix of categories Q to that of R, which forms a bimodule of lax functors. So a lax functor is like a many-object monad, and this is a bimodule between them. And I'm calling this a displayed profunctor. So in the same way that you break up composition in R to get a matrix of transformations, we can break up the actions of Q and R on I to determine matrices of transformations for the actions. So inverse image along a span of profunctors determines a matrix of profunctors. So this equivalence is functorial, and this gives an equivalence of entire double categories between span categories and displayed categories. So these matrices of categories and profunctors will be the underlying stuff or data of the language of Metalogic. But now, as I was suggesting in the introduction, if these spans are supposed to represent relations from A to B, these relations should vary over processes in A and B. We're going to need to have actions by morphisms in A and B. So the question is, how does a category form a double category so that we can define an action? So the arrow double category is the double category in which a square is a commuting square. And we distinguish between the vertical morphisms and we distinguish the horizontal ones by this hat here. And these squares compose both vertically and horizontally, which means that as double categories, they are monads in spans of categories. And so we can define an action on a span like R. When you do that, for free, you get the notions of fibered category and op-fibered category. A fiber category is a left module of arrow double categories, and op-fibered is a right module. And the way to read this, just focusing on the bottom half here, if you have a morphism from A0 to A1, and you have something lying over A1, you can pull it back to get something lying over A0. This is the contravariant action that people are used to in a fibered category. This is usually denoted A star R and usually called something like pullback. But here we're just denoting it as composition because it really can be understood as composition in a double category. And dually for op fibrations here as a push forward action. So here is the equivalence to the usual definition of fibrations in terms of Cartesian morphisms. And I believe that the visual language can really simplify the intuition behind these structures. However, a lesson that I learned the hard way, it turns out that an arrow double category is not a logic. It's a double category with companions, but not conjoints, because we do not have any backwards pointing morphisms. And it turns out that that actually introduces a limitation to the equational reasoning of an arrow double category. Essentially, there are certain composite equations that cannot be expressed without backwards pointing arrows, specifically for the associativity relation between composable pairs. So, long story short, you need arrows to point both directions in order to define this structure. So we define the weave double category to be the coproduct of the arrow double category with its opposite. And by opposite, I mean horizontal opposites, just the horizontal mirror image in which we have these backwards arrows and backwards squares. We can denote the arrows by the hat and an op arrow by check and a bar for either an arrow or an op arrow. So the idea is that an action by this weave double category will be a bifibration rather than just a fibration or an op fibration. We'll have both pushing and pulling actions. But real quick, where are we forming this coproduct? Well, how exactly is this constructed? Let double A be the two category of double categories on A, and just fixing the base category and just considering the two category of double category structures on A. And in this two category, we can define the weave double category to be the coproduct. And it turns out that this coproduct can be understood simply as a union of double categories. It's generated by squares of the arrow double category, squares of the op arrow double category, plus isomorphisms between their identities. This is the only like subtle part of how to take a union of double categories, is that you need to unite their identities so that you have one identity that works for any kind of composition. So once you do this, this double category is indeed a logic or a bifibrant double category because we have both companions and conjoints. And the modules of a weave double category are bifibred categories. Now, this is what we need. This is all the infrastructure we need to begin defining the underlying structures of logics. So a matrix category, or two-sided bifibration, is a span of categories, which is a bimodule from the weave of A to the weave of B. And these actions can be drawn as follows. The idea is that we have both a push and a pull action by both categories. And here I'm drawing it as like an arrow pointing both directions to represent either an arrow or an op arrow. So this is why it's called a two-sided bifibration, but I just wanted a shorter name for matrix category. So because we're defining this higher dimensional algebraic structure, it's a weak bimodule. So it is associative and unital up to coherent isomorphism. And believe it or not, every little detail can actually be faithfully interpreted visually. The naturality of the associators, the coherence of the associators and unitors, and the pentagon identity and the triangle identity, it turns out that all of it can be visualized. And also, you might notice that these coherences precisely correspond to defining composition of a double category. And in fact, the collage of a matrix category is a bifibrant double category. So these are the HOMs of logics and horizontal profunctors between them. But we also, because logics are two-dimensional structures, we also need vertical profunctors if we want a complete metalanguage. And as far as I know, this has not been defined or explored. And so essentially, the notion of a relation between vibrations can be defined in a completely analogous way. So in the same way that a category puffs up into two dimensions as the arrow double category, any profunctor F from X to A defines an arrow profunctor, which again consists of commutative squares. It's just that now they involve heteromorphisms rather than morphisms in a category. And this these squares again compose horizontally, and you have horizontal units. So this forms a monad in spans of profunctors. So again, we can define actions by this arrow profunctor. But again, there are some issues if arrows only point both directions. So again, we form this union with the opposite to define the weave vertical profunctor. And once you do that, we can define a matrix profunctor to be a span of profunctors with, again, a bimodule structure of these weave profunctors. So the pictures are exactly the same, except now we're thinking about heteromorphisms between categories. And this is a very rich structure because it's a fully two-dimensional bimodule. Because it's already a span of profunctors, you already have a vertical action, but now we're also defining a horizontal action. And because of this, it has interesting coherence. It doesn't make sense to say that it's associative or unital because its source and target are associative and unital up to isomorphism. So instead, we say that the associators and unitors are natural with respect to the actions of the weave profunctors on this span of profunctors. So this is going to be the underlying structure of vertical profunctors between bifibrant double categories. Now, similarly, those two constructions are functorial. So similarly, we get the concept of a matrix functor as a morphism of weak bimodules. And again, we can understand this as a map from inner to outer. These are going to form double functors and transformations between horizontal profunctors. And these preserve composition and identity up to coherent isomorphisms. So this on the left, you could understand as an invertible laxor or lax structure as a map from f of A, well, you can see it right here, pushing the action inside as a lax structure, read from top to bottom here, and similarly on the right action. And similarly for matrix transformations between matrix profunctors. Now, the crux of this whole construction was in defining composition of matrix profunctors. The tricky thing about trying to define a relation between dependent categories is that when you compose, you're composing over profunctor composition, which is a quotient. So a composite matrix profunctor will be indexed over a quotient so that your indices are only determined up to associativity. So recall that in a composite profunctor, F composed G, the elements are equivalence classes up to associativity. So two pairs are equivalent if there's a zigzag of morphisms in the middle category that reassociate one to the other. So this is why we needed morphisms to point both directions. This is why arrow double categories are not enough. Fibrations by themselves are not enough, and we needed these weave double categories and bifibrations. So once we do have that, we can represent these zigzags that reassociate from one composable pair to another. And in fact, it turns out all that you need to ensure is that this is well defined over the identities. So if we have some matrix profunctor M here over F and K, which remember represents squares, one matrix category R is representing loose morphisms, one for S, and now this matrix profunctor M is representing squares. And our actions are representing horizontal composition. So in fact, what we need to do is to make sure that actions are well defined over the identities. So inside the composite of F and G, these associative zigzags look like identities. But now if we're trying to index over that quotient, those zigzags would be doing a lot of pushing and pulling of the middle matrix category. So we need to impose a quotient that says all of those reindexing zigzags we are going to consider as just acting as the identity. So that quotient can be specified by a certain coequalizer. And once you do that, matrix categories do indeed form a logic or a bifibrant double category. And moreover, it forms a double fibration over pairs of categories. Basically, there is a substitution structure of functors in matrix categories and transformations into matrix profunctors. And this composition that we just defined gets along with that substitution. So, so what we have done is defined this middle slice here. We've defined the logic of matrix categories and matrix functors, which is this vertical part here, and matrix profunctors and matrix transformations, which is the whole cube here. And now to complete the three-dimensional structure, we need to define parallel composition of matrix categories.
Christian, would you be able to finish this up in maybe 2 minutes or so?
Yes. Yes, maybe like 3 or 4. So essentially, as I was saying in the introduction, composition of these matrix categories is a weaker version of a coend. So we, instead of quotienting for associativity, we adjoin a coherent associator isomorphism by something called an isocoinserter. And then we impose coherence of that associator by coequifiers. And this forms what is known as a codescent object. And similarly for composition of matrix profunctors. The surprising thing at the end, everything is working nicely, but the surprising thing is that parallel composition does not preserve sequential composition. It's neither lax nor collax, and there's a real obstruction in both directions. And I'm happy to talk more about that. This is a fundamental obstruction to this whole construction. So the structure that we're getting can be understood as a bifibrant triple category without interchange. So because parallel composition is not a double functor, essentially we break everything up into its one-dimensional pieces and define the three-dimensional structure on that data. So matrix categories form a metalogic, a triple category without interchange. And once you've done all this work, then you can say that a logic or bifibrant double category is a pseudomonad in MatCat. And there's a fully three-dimensional pseudomonad construction, which constructs the metalogic of logics. And the main thing that I want to emphasize is that there are two kinds of profunctors between double categories. And I think therein lies much of the complexity of category theory. So that is the construction of my thesis, and it generalizes in various ways. But I do believe that in a certain sense, this is a unified metalanguage of category theory. And I think that there is a huge research program here of unifying category theory that's just waiting for people to explore. So I am looking forward to collaborating with people. Thank you.
Thank you, Christian. And let's also thank Christian with a virtual applause. And thank you for a very nice talk, very interesting.
Thank you.
Lots to explore there. And let me just ask, are there questions, comments?
Yeah, I have a question, maybe a
Yes.
naive one. But so you say that this is like a sort of a sufficient to model category theory. My immediate instinct coming from higher category theory is always to ask, all right, well, like, maybe like take things up one more level. If, for instance, you thought about like the theory, like sort of two category theory or bicategory theory, would you expect that you would sort of level up to like a sort of four upple like category or something like this? Can you see how that might happen?
Well, short answer, yes. I can see how this would generalize to arbitrary dimensions, but I don't know if it will be necessary. I don't know. I think that somehow, like when I don't know much about higher category theory, but when I read about it, it seems like a lot of it is using the language of space-enriched categories. So like the objects that you're studying are higher dimensional and more general, but still the language that you're using is still the language of these bifibrant double categories. Like I don't know much about the subject, but when I look at like Emily Reel's infinity category theory from scratch, toward the end of it, I noticed that they're still using the language of virtual equipments, just applied to certain space-enriched categories. So I think that there might be a way that we can have a complete kind of self-contained language is my hope, but I do also think that this construction generalizes to any dimension, and I'd be happy to talk about that.
Yeah, I imagine that like specifically, I guess one last comment I make, like with Emily Reel and like Barady's work on infinity cosmoi, where they kind of turn a lot of theory of infinity one categories into category theory, synthetic category theory. Again, yeah, I guess like your theory could be like a meta language for that kind of world as well, just maybe space enriched. Yeah, so that'd be really cool to see.
Yeah, exactly. Thanks.
Are there other questions? Brandon?
Hi, thanks, Christian. So two quick questions. And maybe this first one is just me sort of missing. So at the end, you talked about how like really trying to unify things in category theory using this language. Could you maybe just say quickly like what types of things you want to unify? I'm sure you already mentioned it, but
oh well. What I'm trying to claim is that like this subject of formal category theory that people have known about for a few decades now, from what it seems like to me, it really does abstract and unify the basic notions that we're using when we do anything with category theory. Like monads and comonads or extensions and lifts. All of those basic notions can be are expressed in this language. So I'm not right now. I'm not sure what is outside of the scope of this language. So if you have ideas of what could be somehow outside of it, I'm interested. But right now, I don't even know what can't be expressed in. I understand that some things form, a virtual equipment rather than a regular equipment, but this framework also generalizes to that in the polycategorical generalization.
So correct me if I'm wrong. Then when you say unify, you mean that like these fundamental aspects of category theory can be realized as like certain standard constructions in this language.
Yeah.
Okay.
Like I think right now there has been this perception of category theory as like a big decentralized network of interrelated concepts. And I'm trying to propose that this structure that we currently call a pro-arrow equipment actually is kind of a central ground for all of these concepts. And that there is a coherent meta language of all of those. Does that make sense?
Yeah, so I guess like maybe I could draw an analogy. I understand there's a lot of reasons why yours is more powerful than this, but like in the sort of classical, like all concepts are con extensions, would it be a valid analogy to say that like, okay, that's sort of saying that con extensions are a meta language for, you know, adjunctions, limits, and whatnot?
Yeah.
Okay, I think I get what you're saying then. My second question should be even shorter, which is where can I read about this?
Yeah, so I posted the slides in the chat, and then they'll also be on the Octoberfest site, and then soon it'll be on the archive. But right now it's at this link here.
Great, well, looking forward to it. Thank you.
Thanks.
And Jean-Baptiste.
Do you hear me? Yes.
Yes.
Yes, I would want to know if you think that your graphical language really helps to prove stuff. Because my question is not about the whole categorical structure, but is it easier to manipulate all these things with your graphical language than using commutative diagrams or equations? Because for me, it's a bit difficult to visualize the things with all the colors, but so I'd be glad if I was seeing an example where you show that it's really easier to use the drawings for proving something, or I don't know.
Yeah. So I guess what I want to communicate is that it's not an either-or choice, because the visual language is dual to syntax. They're literally geometrically dual to each other. They fit together. So it's not like a choice of one or the other. It's actually, they complement each other. Yeah, basically, I think once you get up to 3 dimensions, for a lot of people, it becomes very hard to keep all of that straight in your head, especially if you don't even know like a canonical standardized layout of the cubes that you're thinking about. It becomes very hard for a lot of people. So one thing that this provides is a standard layout of modifications. These are what are currently known as modifications between double functors. So at first, it's just kind of a general systematizing perspective, and that, like, for me, it was the only way that I was able to like wrap my head around every step of the construction. But in terms of, I mean, because my thesis was just setting up the infrastructure, I haven't started to use this to start proving stuff. But like, I believe that the like extensions and lifts will have a certain like bending backwards notation that will be very intuitive. But at least so far right now, it was just how I could wrap my head around like the definitions of, you know, two-sided bifibration and profunctors between those. Because people have been using dependent categories for a long time, but surprisingly, we hadn't, as far as I know, we hadn't made the relations, a functional notion of relation between those. So this is an example of a concept that was discovered because of the visual language. Yeah.
Okay, thank you.
Thanks.
Any other questions, comments?
Maybe one other one. Just you mentioned before, like this is a sort of meta logic, and these are logics. Can you maybe, and you mentioned something about a higher order logic earlier. Can you maybe like, do you have some like very formal statements about this being precisely a logic, like rather than like a model for?
Oh, well, so I guess this is just kind of like an interpretation. It's like just, a new shorter word that suggests like kind of a simpler philosophical interpretation of this structure. But it does align with how currently, we model type theories using fibrations. So the idea is that the horizontal morphisms in squares are dependent types and morphism in terms of dependent types. So you really can read this like how we currently use, judgments and inference rules in logic. So it does align with that use of the word. But yeah,
it would be interesting then to see, because we have this interpretation almost up to like dimension like 2, I guess, of your sort of system. But like I don't know of anything, like, I mean, I'm not a type theorist really, but I don't know of anything in type theory that corresponds to your dimension 3. So it'd be kind of interesting if you had some analog of that.
Yeah, I'm not sure. I'm just understanding it as meta logic, because
Sure.
the vertical profunctors you understand as containing processes between logics, and horizontal profunctors contain relations between logics.
It's certainly not a critique. It's just like a interesting question, or prospect, I guess.
Yeah. Basically, just in metalogic now, your judgments are entire systems of inferences in a logic. And then your rules now are maps between these systems of inferences. Yeah.